so welcome everyone. I just wanted to thank you guys for joining us. As you can tell, I'm not Attila. Attila is in Hungary right now visiting family. So I'm going to be going through the presentation with you. I'd like to thank JF for taking the time to do his talk with us. JF holds a doctorate in earth science, and his doctorate studies were completed in collaboration with the Geological Survey of Canada. He has since worked since 2013 in the mineral exploration industry and is currently the VP of Exploration of Red Pine and the Chief Geo of MacDonald Mines Exploration. I could pass it over to you, JF.
Okay, sounds good. Just gonna share my screen now. Thank you, everyone. So the presentation I'm gonna do right now, this is a presentation that has been done at the GAC of 2022 last year, and also as part of the short course that was given at the GAC on these mineral system, metasomatic iron and alkali calcic mineral system. The objective of this is trying to visualize and present the diversity of mineral deposits that are possible within the system, and also to get an overview of the different mineral assemblages that are characteristic and associated to each of these mineralization styles, and how we can frame all those alterations as fascies of alteration, and how we can relate those after to specific types of mineralization. I will also want to do some publicity as part of this. We recently published the special paper 52 of the GAC. A lot of the concept presented in this presentation, the baseline of all these concepts is presented within this special volume of the GAC. So if there is more question, if you want to have a lot of field pictures and a good exposure to all different alteration types or deposits, it's a very good place to go and to visualize and see the diversity of these mineral systems. The outline, first, because MIEC is somewhat of a new concept, we're going to try to define what it is and why it's potentially a preferable word instead of IUCG system. And after, what we'll do is that we'll see and we'll try to establish with all the different deposit types that are possible in these metasomatic system, can we try to put together a classification in order to provide a framework and explain why there is such a diversity in these large hydrothermal systems. It's important because then after these tools can be used for mineral exploration and help in the recognition in different geological province of that potential. And the following part of the presentation really is going to cover the different alteration fascies that are possible within these large hydrothermal systems, and see how these fascies can be related to different types of mineralization, and also how can we use certain alteration fascies to predict potentially what type of mineral deposit can be formed in certain areas and zones of these mineral systems. And we'll just see what we can do with hybrid deposits, because these systems are very often polyphase with a component of remobilization. So necessarily we can get deposits with multi-stages of mineralization and alteration, getting complex hybrid. And we'll use a nickel deposit as an example. Nickel is an example from Canada. So what it is, metasomatic iron and alkali calcic mineral system. It's a combination of different words, and these words were used to represent the processes underlying the formation of these hydrothermal systems. The first one is metasomatic. Metasomatic because one of the characteristic features is extremely strong to intense metasomatism. So what it means is that regardless of the type of host rock, we can circulate enough fluids and then completely transform the primary attributes of these host rock, and to create an hydrothermal rock that of which the composition has nothing to do with the original rock types. Iron, this is a very ubiquitous and important characteristic of those systems. as the development of iron-rich alteration facies is a very typical attributes of that. One thing important though is that iron can occur as different minerals. Iron oxide is the one that we are the most familiar with, or the one that really, because of IUCGs that are possibly formed in the system, typically associated. But it's important to consider that in certain instances, depending on the composition of the geological sequence, the chemistry of the fluids that are involved, different types of minerals can be formed as well. Iron minerals, that includes iron silicates. So sometimes this iron-rich metasomatic activity or alteration types are going to be expressed as iron silicate, iron sulfides, and iron carbonates. So there will be iron zones of extremely strong iron oxide alteration, but there can also be an association with strong iron silicate, iron sulfide, and iron carbonate alteration. Putting this understanding into an exploration program can become quite important, because a lot of the geophysical methods that we're using for targeting mineralization or potential zones of mineralization are based on the expression of iron in the crust. So basically, we're trying to get a proxy for an accumulation of iron. And if we use magnetism, for example, but mineralization is primarily associated with iron silicates and not iron oxides, then we may miss that zone of mineralization. Same if it's primarily associated with iron sulfides. For iron sulfides, instead of magnetism or gravity, electrical methods can become a key way of targeting zones of mineralization associated with this expression of iron-rich metasomatic activity. So it's something very important to keep in mind when looking at these systems. And that's why we put iron instead of iron oxides in the name of the system, to remove the emphasis on iron oxides. They're important, but there can be other types of expression of iron-rich alteration. Alkali, and calcic, because when we have these zones of iron-rich metasomatic alteration, generally it would come with either alkali metal or alkaline earth metals. And the ones associated with iron can become a very good predictor for the type of mineralization that can be formed. So having potassium with iron, for example, doesn't have the same significance as having calcium or magnesium with iron. So this is to integrate as well this component of these hydrothermal system. And then the other alkali metal that is extremely important, especially for the regional recognition, is sodium. And this encompasses the extremely strong zones of sodic alteration that are possible as well in these hydrothermal systems. So metasomatic iron and alkali calcic mineral system, it's potentially a preferred alternative to IUCG system. One of the key reasons is that MIEC, it's better encompassing, for the reasons cited before, the wide diversity of base, precious, and critical metal deposits that are possible in these hydrothermal systems. But also, it is illustrating the suite of metasomatic reactions that are forming different alteration facies and mineralization. So as I mentioned previously, iron with permutation of alkali and alkaline earth is really what can help us to figure out where we are within these hydrothermal systems and what is the potential significance in terms of metal assemblages that can be formed in these zones of alteration. They're extremely large hydrothermal system. They can cover areas extending over hundreds to thousands of kilometers. And their formation, from the understanding that we're starting to get right now, seems to be driven by the physical-chemical evolution of an extremely large plume of fluids that is interacting with a wide range of host rock. And the interaction will depend on the composition and also the main permeability zone present in the geological province. It's generally, or these provinces affected by these metasomatic and alkali calcic hydrothermal system are generally located along major crustal discontinuities. So having a contact zone between two terrain or two crustal blocks of different age is generally a good place to look. They can be proximal to distal to large and compositionally evolving magma chambers, and this will be typically formed in a continental setting. And also importantly, and this may also be part of the reason why we see such a diversity of metals in these mineral systems, is that they are formed under evolving geodynamic settings. Things are not set in time, and the dynamic is evolving, and so could the metal assemblages, as the fluid plume is compositionally evolving as well, as it's reacting with a lot of host rock as it moves through the crust. And then deposit and joins in these systems will tend to cluster in a series of districts. So there's going to be often clusters of deposits showing within these mineral systems. For the metasomatism, I think this provides a good example of how extremely strong fluid rock reaction can completely transform the mineralogy and also composition of a rock. So starting with the porphyritic andesite and then circulating fluid into that andesite. And as this fluid circulation is happening, the composition of this original andesite, but also the texture of the andesite are becoming progressively more destroyed to the point where we have a pseudopegmatic textures. And then we have this original andesite, instead of being composed of a fine-grained matrix with the phenocryst of plagioclase, we have a matrix of amphibole with large lat of extremely strong sodically altered relics of host rock composed of very fine crystals of albite, and then with a mix of magnetite and apatite as well, filling that matrix. So really a complete transformation, but also recrystallization of this andesite with fluid rock interactions. In terms of distribution of these systems, so they can occur on every continent and rocks of different ages as well. And the stars are illustrating the systems that we will use example in the presentation to show different styles of mineralization that are possible. So going to the north of the country in the Great Bear Magmatic Zone, on the eastern part of the country with the Central Mineral Belt, the Greenville Province, the Southern Province, in the United States, in the Idaho Cobalt Belt, in Brazil, the Carajás District, in Australia, in the Cloncurry District, and also the Gawler Canton, and then in China as well. Some examples are going to be presented. If we look at the evolution of these metasomatic systems, so if we look at the evolution of a metasomatic iron and alkaline calcic alteration system, there is generally a relatively systematic progression in the type of alteration that we can see in the rocks as the fluids are interacting and the fluid plume is compositionally evolving. It goes from the heating stage where we can form extremely large corridors of sodic alteration, generally resulting in the formation of albitites. And then also, if there are carbonates in the environment, skarn assemblages can also be formed. And then one of the characteristic feature when these systems are starting to get some intensity and we start really to get the signature of the fluid plume, it's generally an extremely strong addition of iron that becomes present in the system. This addition of iron can be expressed as different mineral assemblages, but the ubiquity will be the addition of iron. And then we can form a succession of fascies of alteration, and then each of these fascies will be associated with different assemblages of metals. But iron is going to be the key component that links them all together, from high temperature fascies to progressively lower temperature alteration fascies. As it gets to the lowest stage, lower temperature stage, there's also an increase in the complexity of the mineral assemblages that can be formed, but also an increasing diversity of the type of mineral deposits that can be formed as well. And this is why there are much more elements that are present in association with iron at this low temperature fascies compared to the higher temperature fascies. Temperature is probably peaking in here in these metasomatic system at about 800 to 900 degrees Celsius. Something now that is emerging as well is that we know we have this succession of alteration facies in which iron is a very important component, but also what we are observing, especially if we go in the Cloncurry district, but also in some of the Canadian settings like the Southern Province, but also the Romanée Horst, is that there is a succession of alteration that don't have iron as the key component, but these facies of alteration are still part of the evolution of the hydrothermal system. It's important to consider those as well, because as it's exemplified in the Cloncurry district, it can also lead to the formation of significant zones of mineralization. In terms of terminology, the ones that have high iron, we can label them iron and alkali calcic alteration facies. And then in order to group deposits, this is also important because we can then group deposits based on that commonality, which is a systematic association between iron enrichment and the deposition of metal. So these iron and alkali calcic alteration facies can be forming metasomatic iron type deposits. And then these alkali calcic alteration facies, so those in which iron is not a predominant component, it can be there, but it won't be extremely abundant. They can form metasomatic alkali calcic deposit because still the alkaline earth and the alkali will remain extremely important component of the different types of alterations that are possible in association with the mineralization. Just here to exemplify the diversity of mineralization styles, but also of these alteration facies that are possible in these systems. And then just illustrating this sequence for the iron and alkali calcic facies that we just see. Here we have this progression from the initial sodic alteration, which is generally the first facies observed in the development of these systems. Then to the progression where we start to add iron, when the fluid plumes start to add iron in the formation of alteration. And then we can have skarn iron types of alteration facies. And at this stage, we can start to precipitate scheelite in association with this enrichment in iron, so magnetite and iron clanopyroxene. And we can start forming tungsten mineralization, where there is a flooding of iron in the hydrothermal system. And then at this stage, we can start forming iron oxide apatite or iron oxide mineralization. So IOA type mineralization, in this case with magnetite, and then in association with apatite. New emerging type of mineralization that can exist in these metasomatic systems, hydrothermal nickel with some cobalt and also a copper component, exemplified by the Jaguar deposit in Brazil, where we have, in conjunction with magnetite, the deposition of sulfites, nickel sulfites, and pyrite or pyrrhotite, and then also associated with apatite, evolving to assemblages of amphibole biotite magnetite, an association generally with sulfarsenide, and then a gold cobalt with sometimes bismuth or copper association. This is exemplified by the Nico deposit, or biotite-rich type of alteration facies. And in this case, there won't be any iron oxide, so it will be an iron silicate type of alteration. And biotite will be the key iron-rich mineral. This is very ubiquitous in the mineralization of the Blackbird district in the United States. For example, the Murrell deposits, where peak cobalt mineralization is associated with the development of that biotite tourmaline alteration, to the formation of Sensu strictu IUCG mineralization. So this is an example of magnetite group IUCG mineralization, where we have this matrix of magnetite. Then the fragments and class in those breccias are being potassically altered as the magnetite is forming in the matrix. So this is forming something that we can relate to IUCG deposits. Hematite group IUCG mineralization. So this is another example from Permanent Hill, where we have, in this case, hematite and sericite and siderite forming the matrix, but also altering some clast with the depositions of the copper sulfide. In certain instances, especially when these systems are developed in reducing geological environment, instead of having iron oxide, iron sulfides are going to be preferentially stabilized, and then it's going to form, instead of iron oxide copper gold type of mineralization, it's going to form iron sulfide type copper gold mineralization. They're kind of equivalent at low temperature, especially for hematite group type mineralization and iron sulfide type mineralization. Just the expression of iron metasomatic activity will be different. And this is an example from Delhi Pacific in the Romani Horst in Canada to formation of gold-rich type of mineralization. In this case, it will be primarily an iron silicate type of gold mineralization with its association with chloride. Some sulfides can also be variably present. And this is exemplified by the scanning deposit located in the southern province in Canada. So this provides kind of an illustration, first illustration of the potential of the diversity of metal assemblages and mineralization styles that are possible in association with these iron and alkali calcic alteration fascies. It really illustrates the broad range of deposit type that are possible in these hydrothermal systems. And now, if we go to those that don't have any iron, but are still a component of these systems, so the alkali calc, those associated with alkali calcic alteration fascies, we have an example here from the Romani Horst, where we have a chloride carbonate sericite assemblage associated with uranium and gold that is overprinting albitite in the Romani Horst. In the southern province, at the Bristol Breccia, we have an albitite. This is just located just west of the scanning deposits. We have an albitite that is overprinted by a matrix of quartz with variable ferrous dolomite and some pyrite. And this will be associated with cobalt, gold with subsidiary cobalt mineralization. An example from Australia, the Tekel deposits, overprinting albitites again. Then there is a deposition of gold in association with some quartz veining, forming a lower iron type of gold-rich deposits. And the Palkovitz prospect, again from the southern province. In this case, what we have is we have an albitite that is variably overprinted by ferro and dolomite with a subsidiary quartz, some disseminated pyrite, and then this is associated with gold mineralization that is overprinting the albitites. If we try now to group these different mineral deposits that are possible in these large metasomatic systems, first starting with metasomatic iron deposits, one underlying concept to support that grouping would be the universal association between primary mineralization and iron and alkali calcic alteration fascies. So in order to have a metasomatic iron deposit, we need to have an extremely strong or the abundant formation of iron minerals that occur in mineralization. Iron minerals can mean iron oxides, so hematite and magnetite, but this can also mean iron silicate, and then there's a wide diversity of iron silicates that are possible. And depending of the host environment, if the host environment has a good buffering ability, this may initially hinder the formation of iron oxides, and iron silicate can be extensively formed before the system really saturates and then start forming iron oxides. For example, mafic environment, they have this good buffering ability. Our carbonate sequence and also sedimentary sequence seems to also have a stronger buffering ability, and then they can form a lot of minerals that can accommodate iron before actually starting to form iron oxides in the mineral system. Iron carbonates can become, in certain cases, an important component in the expression of that iron-rich metasomatic activity. And iron sulfides especially in areas that have a lot of reduced units. This can help to preferentially stabilize iron sulfides over iron oxide, especially if sulfur is also available in the geological sequence. For example, geological provinces that have a lot of graphitic schists seems to preferentially form in certain instances iron sulfide mineralization instead of iron oxide mineralization, because the graphitic schists provide this reducing environment, and commonly there are sulfides precipitated within them that can be incorporated in the fluids and then stabilize preferentially the formation of iron sulfides instead of iron oxides. These deposits would be structurally controlled, epigenetic, form in continental setting, and they will be temporarily, not necessarily closely spatially associated with significant magmatism. And then here, it could be a representation of the different classes of deposits that are possible, going from tungsten, iron, rare earths, nickel, cobalt, copper, uranium, and gold. All of these can be part or are part of the same evolving metasomatic system. With the metasomatic iron copper deposit, a type can become IUCG deposits, magnetite, hematite to hematite group, and iron sulfide copper gold deposits, for example. Depending of the type and the class of deposits, they can have variable size and grade. And then the class should be defined by the primary economic metal in the mineral resources, whether it's estimated or anticipated. For example, if it's a mineral showing or a prospect, then we don't exactly know what a mineral resources could look like. But with the chemical analysis, we could have a good idea what the prevailing or the most interesting metal could be. Very often, we can see polyphase mineralization or associated with polyphase alteration in those deposits, even at the scale of a showing. In this case, it should still be based on the most significant metal in the resource. Polyphase alteration in mineralization, though, it's generally a very good process. So it's good to see that in a geological province, because this can really diversify the metal assemblage of the deposits. For example, if a metasomatic iron cobalt deposits is overprinted by an event that can form metasomatic iron copper deposits. So for example, IUCG magnetite group type mineralization. And instead of having cobalt and gold, then we can start having cobalt, gold, and copper. But then the classification really depends on which metal remain prevalent in the mineral resource. Polyphase alteration and mineralization is also good, because if new fluids are interacting with pre-concentrated metals, these metals can potentially be remobilized and concentrated as a fluid are recirculating, dissolving and reprecipitating the minerals, and then they can at the end concentrate certain metals, and this can benefit the economics of certain zones in these deposits. Just to address the IUCG types deposits, IUCG is a very significant and important type of mineral deposits that are formed within these metasomatic system, but it's important to frame IUCG deposits where they belong as well. It's a type of deposits that is possible in a very large metasomatic system. They're still extremely significant because right now they're the largest deposits that are currently known in MIEC systems. But in order to classify something as an IUCG deposit, the zones of mineralization, they must match certain criteria. It's important not to classify everything as IUCG, because not everything is an IUCG. There are sensu stricto IUCG, but there are also other types of mineralization zones that are not IUCG, and they should be then classified as what they are, not as IUCG or IUCG-like or IUCG-related, because then this kind of blurs the relationship between these different mineral deposits and zone of mineralization, and makes it difficult to evaluate the fertility, but also the potential of certain areas of these large metasomatic systems. So in order to classify something as an IUCG, we need the association of copper-gold mineralization with the formation of iron oxides. And then copper will be the main metal in a mineral resource, and gold and also silver or uranium can be byproducts of copper. They're hydrothermally and structurally controlled mineralization. And something important is that they must have a significant component of iron oxides in zones of mineralization. So it's iron oxide copper gold mineralization. So we need this component of iron oxide in association with mineralization. And then they will be hosted in much larger zone of alkali calcic and iron and alkali calcic alteration zones. For IUCG deposits, we have two end members, magnetite groups, IUCG deposits, and hematite group, IUCG deposit. And then there is a transitional group of magnetite to hematite group. So one example of a sensu stricto IUCG mineralization from the Ernest Henry deposits, where again we see the accumulation of iron oxide in association with copper sulfide and potassium alteration, preferentially partitioned inside the fragments in that matrix. And then hematite group IUCG mineralization in the Olympic Dam deposits, where we have this extremely strong iron metasomatic activity, where these rocks are being completely replaced by specular hematite in association with the deposition of copper, different types of copper sulfides. For the metasomatic alkali calcic deposits, this group is much less well constrained than their iron-rich counterpart. The reason why is that they haven't been, their association with these metasomatic systems hasn't been as well constrained as the other group. We know they are related to these metasomatic systems because of their age, their relationship with zones of sodic alteration, and their close spatial association with their iron-rich counterpart, but they haven't been as well recognized as the iron-rich ones. We can still find a few across the world that we can start associating and then start to do some grouping based on the deposits that are known to be associated with these metasomatic systems. A group that is gold-rich, one example could be Tequil in Australia. One group that is potentially uranium-rich, with examples of showings and prospect in the Romane-Horst in Canada. A group that is rich in copper, Mont d'Or in Australia would be a good example of that. A group that is rich in molybdenum, with the Merlin deposit in Australia being a good example of that. And potentially a group that has rare earths, but also uranium, maybe Marie-Kathleen, but this would remain to be confirmed. Another possible class is cobalt, but more needs to be done in order to confirm that cobalt deposits can actually be formed. It's possible, but remains unproven. And then what defines this metasomatic alkali calcic group of deposit? There is an association between primary mineralization and alkali calcic alteration facies. So we can have the formation of iron minerals, but it won't be a significant formation like in their iron-rich counterpart. Some of these alkali calcic facies will be quartz-rich, some will be carbonate-rich, and others will be silicate-rich. And there seems to be an association between quartz and certain metals, carbonate and certain metals, and silicate with certain metals. They will be temporarily related to non-metasomatic iron deposits or the formation of iron and alkali calcic alteration facies in the geological province. So this temporal relationship is extremely important in order to classify something as metasomatic alkali calcic mineralization, because this really provides a relationship between the two groups. They'll generally overprint albitite corridors that are the first manifestation of the development of these hydrothermal systems. Comparable to the iron-rich one, they'll be structurally controlled, epigenetic from a continental setting, and they will be temporarily associated with significant magmatism. They can be of variable size and grade, and then, like the iron-rich one, the class of deposit defined by the primary economic metals. there will be hybrid deposit and comparable to the iron-rich one. It's good to see polyphase alteration and mineralization at the scale of a showing to the scale of a deposit. I'm just presenting here a way of visualizing alteration using molar proportion of major element. This is useful in order to evaluate the type of alteration facies that can be present in host rock and help to associate different facies of alteration with different metal assemblages, but also can help to understand where we are within these systems. The color coding is also important because it kind of match generally the visual expression of these different styles of alteration that we can see in host rock. I'm presenting it here too because in the next slide, it's going to be used in order to define the chemical attributes of certain facies of alteration and their association with the specific metal assemblages. So we use pink for sodium to light pink because very often albitites, they can be white, gray to light pink, green for amphiboles with calcium, black for the iron oxides, bright red for potassium, which is in which K feldspar is very often bright red, magnesium for the light green of chloride, but also for diopsides in certain scarlet assemblages. This is the standard barcode that can be used, but then if other elements are added, then more information can be extracted for the type of alteration, and then the type of alteration and the chemical associations that are possible. This becomes especially important in lower temperature alteration facies. So if we look at the chemical signatures of the metasomatic iron deposits and zones of mineralization, one thing that we can see using the barcodes, those without silica and those with silica, is that the iron component is really the key component in association with metal enrichment, whether it's Jaguar for nickel mineralization, Merle in the Blackbird district for cobalt, Nico for gold, bismuth, and cobalt, and the Henry, IUCG for copper, Kalman, which is an ISCG in Australia for copper. In this case, iron is expressed as iron sulfides, and then Scadding for gold. Here, iron is expressed as iron silicates. And then when we look and compare this signature, this iron-rich signature, to the metasomatic alkali calcic type of mineralization, what we can see is that iron can still be present, but it is not as prevalent in the chemical signature using the barcode system as for metasomatic iron deposits. For the Palkovitz gold mineralization, overprinting in albitite, for example, and for the Merlin deposits where there is extremely strong K feldspar alteration associated with molybdenite position. The next slide is what it's going to be. We're going to breeze through that a bit more quickly. It's just going to present a visual example of the different blocks and different facies of alteration, going from the early stage sodic alteration and then progressively building the evolving chemistry of the fluid plume, and then the different alteration facies that are resulting from that evolution, and the style and type of mineralization that results from that chemical evolution. Starting with the sodic and skarn alteration, and really the aiding stage and ground preparation of the systems. And here we have an example of sodic alteration in sedimentary rocks of the southern province. And we can see that when sodic alteration is intensifying, the primary textures of the host rocks are becoming completely destroyed. This was initially a bedded sedimentary unit. When we look at what happens when we're doing extremely strong sodic alteration, so we start with a host rock, and regardless of its composition, generally we're having a ristite, which is an albitite. So the major minerals from during sodic alteration are generally albite, and then there can be a variable residue of quartz, some accessory minerals with different, like element like zircon, they can remain immobile, but being relatively enriched by the depletion of everything else. Same with other high field strength elements like tantalum and niobium. Sometimes titanium can stay behind. Sometimes phosphate as well can relatively stay behind. But in certain instances, all of these elements can also become mobile during sodic alteration. And then everything else is destroyed. So any other primary silicates and sometimes even carbonates, they're completely destroyed. And then we have this risk type of albitite as the sodic metasomatic activity is progressing. Albitites are extremely important because they prepare the ground, but they are also one of the first manifestations that can be seen in a geological province that is affected by metasomatic iron and alkali calcite mineralizing system. They have a regional extent. They'll generally be formed along all the major discontinuities of the geological provinces, and they'll do zone of extremely strong alteration, resulting in the formation of albitite. This is an example from the southern province, where sodic alteration is known for at least 340 kilometers from Bruce Mine to Temagami at least, and potentially extending more. Albitite, though, they can be tricky to recognize. Their visual presentation can be extremely variable, and they tend to be described as many things instead of albitite. Typical descriptors are syenite, felsite, aplite, bleach rock, quartzite, silicification, hornfels, chert, red rocks, and etc. So it's something important when there is a rock that looks, especially in a known province that is known for having the potential for these systems. If there are zones of bleaching, and in these zones of bleaching, the textures of the host rocks are becoming completely obliterated, it would be good to get a fluoracid analysis potentially on these rocks and see, is that bleaching a sign of sodic alteration? Because if yes, then this could suggest proximity to a structure along which fluids could have been circulating. And then the next stage is, if these fluids have been circulating along these structures, can there be zones of mineralization along the same structure? And this is, for example, a typical albitite in the southern province at the scanning deposit. Albitite can also be good for ground preparation because as sodic alteration is generally progressing through a coupled dissolution precipitation, what it tends to do is that it will do the sodic alteration, but then the residual albitite will be extremely porous because this alteration will tend to remove a bit more material than it's leaving behind. And this porosity, especially if we apply stress on these rocks that will become also isotropic, can become very good zone to focus stress and then start initiating the breaking of the zones that are albitized. This can be well visualized using CAT scan images of an albitized sedimentary unit. So on these CAT scan images here, we have the original bedded sedimentary unit. And then these dark beds are those that are completely sodically altered. And what we can see is that all the veining is preferentially formed in the beds that are albitized, but those that are not as albitized and preserve their phyllosilicate-rich composition, they're not broken. They're a bit more difficult to break than these porous and isotropic zone of sodic alteration. So this process happening at a large scale can really help to focus the next stage of fluid flow into these zones of albitite, so they likely will be preferentially broken instead of the rocks that are surrounding them. And then this could also favor the formation of albitite-hosted mineralization. As sodic alteration is happening in this heating stage and ground preparation of these systems, if there are carbonates in the sequence and sodic alteration is happening, sometimes skarn alteration can be adjacent to these zones of sodic alteration in the carbonate-rich unit. In here, we have an example where certain beds are becoming preferentially albitized, and then other beds are becoming preferentially turned into skarn assemblages. Same in here, we have the host rock here becoming albitized, and then this part of the rock becoming transformed into a skarn assemblage. At the thin section scale, we can see sometimes the carbonates are just going to be dissolved and then transformed into sodic alteration. But at a certain point, cyanopyroxene, if there's enough carbonates present in the rock, can start to form in conjunction with that sodic alteration. And importantly, the skarn assemblage will not be associated spatially to intrusion. It's really the heat of the fluids that are driving the formation of the skarn assemblage. As the system is strengthening, we start to see the first sign of iron and alkali calcic metasomatic activity. And then we move to the iron skarn iron type of mineral assemblages, and also the first stage of mineralization that can occur in these metasomatic system. In this case, forming tungsten mineralization. And also it can form iron mineralization. So that will be the one of the first steps. As we form, and originally these kind of assemblage, as the iron-rich fluid derived from the fluid plume start arriving, then they'll start forming magnetite. And if there is enough magnetite precipitated, we can start forming iron skarn type of deposits, where we have an assemblage formed by magnetite in association with cyanopyroxene, as an example here from Northwest Territory in Canada. The other style of mineralization that is possible as we're transitioning to this iron and alkali calcic skarn type of assemblage, in conjunction with this arrival of iron and formation of cyanopyroxene and also magnetite, you can start depositing scheelite, forming tungsten mineralization in association with the development of that skarn assemblage. This is an example from the Nico deposit, where we can see this early stage of skarn assemblage. It is associated with the formation of scheelite. And then as the system is evolving and it transitions to the amphibole stage of alteration, then these paragenesis are being progressively overprinted by amphibole and also by amphibole magnetite. But the initial deposition of scheelite comes with the formation of that skarn assemblage. For the southern province, this may have some significance as well. There is a tungsten deposit in the southern province, which is named the Fostung deposit. The number of the resources are here. And what is interesting, now there is more and more evidence that the southern province is actually affected by metasomatic iron and alkali calcic alteration system. And the Fostung deposits, when we look at the mineral assemblages associated with mineralization, it's a mineral assemblages typical of an iron and alkali calcic alteration facies, with having iron-rich cyanopyroxene, edenbergite, and garnet in association with tungsten. Also, there's a very strong component of iron sulfides in certain areas associated with scheelite mineralization. So we can transition from iron silicate to iron sulfide type of expression for this iron-rich metasomatic activity. And then just near the deposit, there is also documentation of albitites that are brecciated. So it kind of shows that there's a possibility that the significant concentration of tungsten can be formed as we're developing this early scan type alteration in the evolution of those metasomatic systems. As we are getting close to peak temperatures, we're moving to the high temperature calcic, some magnesium and iron alteration facies. And at this stage, we're starting to form a diversity of mineral deposit. We can have metasomatic iron deposit, rare earths, and nickel, with different examples that will be presented in the next slides. Looking at the mineralogical changes first. So what are the typical mineralogy of this alteration facies? Amphibole will be a very important component. Can be variably associated with magnetite, apatite. In certain instances, epidote can replace amphibole as a primarily calcic phase in these alteration facies. Titanite will also be important in certain zones. And if this alteration facies is overprinting earlier skarn assemblages, there can be relics of cyanopyroxene and garnets. For example, here, this is east of the Nico deposit. We can see the early skarn alteration assemblages overprinted by an amphibole and amphibole magnetite type of alteration that is overprinting and completely replacing the earlier skarn type alteration. In terms of mineralization minerals, if we have iron oxide apatite or iron oxide type of mineralization, magnetite will be a very important mineral for mineralization. If we have rare earth mineralization, apatite, and especially remobilized apatites can become an important source, but also minerals for rare earth mineralization. Or for nickel, typical sulfides like pyrrhotite, pentlandite, minerite will be the mineralization minerals in association with the development of that alteration patches. Looking at the presentation, so for iron oxide and iron oxide apatite type of metasomatic iron deposits formed at the high temperature calcic iron alteration facies. This is also the thermal peak of the system. And here we have veins of magnetite, brecciating and albitite to form iron oxide type of mineralization. Here we have veins of magnetite with apatite to form iron oxide apatite type of mineralization. This is from China, from Northwest Territories in the Great Bear Magmatic Zone. And this one too, where we have brecciation of a rock by magnetite to form iron oxide type of mineralization. In this case, the magnetite is also vanadiferous, and this is all forming an iron vanadium type of mineralization. Rare earths, especially if there's abundant precipitation of apatite in conjunction with iron oxide or with amphibole, they can start to be concentrated at this alteration facies. However, if this alteration facies is not remobilized by subsequent alteration type, it's likely that the grades, the rare earth grades, will remain relatively low. So it won't be possible to have total rare earth oxide grades over 1 weight% over large intervals. What is necessary in order to form high-grade rare earth mineralization in these metasomatic system is to have the apatite overprinted, well, the anterior zone of iron oxide apatite mineralization overprinted by a subsequent generation of fluids. And what this does is that this dissolve and reprecipitate the apatites. And as this dissolution reprecipitation process is happening, it tends to liberate the rare earths from the apatite, and then these rare earths can be mobilized and concentrated and precipitated elsewhere in adjacent zones or just overprinting the original zone of iron oxide apatite mineralization. When this process is happening at a large scale, it can be extremely efficient and can lead to the formation of high-grade rare earth mineralization. There is an example of that in Canada. It's called the Josette deposit. It's located in Quebec in the Grenville province. And in this case, the early iron oxide apatite mineralization has been extensively remobilized and overprinted by later generations of fluids. And this has liberated and reconcentrated the rare earths and has formed rare earth mineralization grades up to 12% total rare earths over 3 meters. And also importantly, this is concentrating as much the heavy rare earths as the light rare earths. And we can still see the association with the calcic iron alteration facies. Also importantly, in order to have a good predictor for rare earths in the system, there should be areas of potassic alteration. They may not have to be directly associated with the zones of high temperature calcic iron alteration. They might be spatially adjacent, but it's good to have a little bit of potassium. This would be a good sign that rare earth mineralization could be present in association with iron oxide apatite. And then if there is remobilization of that, high-grade rare earth mineralization can be formed. For the metasomatic iron nickel deposit, example from the Jaguar deposit in Brazil, we have iron oxide to iron sulfide nickel mineralization at the high temperature calcic magnesium iron transitioning to a more potassic facies as well. This is also high temperature mineralization. At temperature are estimated for 400 to 500 degrees Celsius. And when we look at the resulting host rock, so we have rocks made of magnetite, apatite, and this matrix of sulfide associated with nickel. And in the case of Jaguar, this has still formed a significant nickel deposit with the resource number indicated here. And when we look at the concentration of nickel and the chemical signature of that, we can see the calcium iron, but also a component of magnesium in association with that nickel mineralization. And then sometimes it's going to be presented as iron sulfide nickel, and sometimes as iron oxide with iron sulfide nickel. So important to keep that in mind, because if the iron sulfide are prevailing, some methods like magnetism might not be the more efficient to target this style of mineralization. There's another one in Brazil as well. It's named the Jatuba deposit. It's in the same district, the Carajás district, not that far away from the Jaguar deposit. Comparable style of mineralization, iron sulfide to iron oxide nickel mineralization. In the southern province, we may also have an example of that type of mineralization. The grade are still incipient. They're not reaching the intensity of what is observed in Brazil, but we can still see development of the high temperature calcic magnesium iron alteration facies with the formation of amphibole, apatite, and then the iron component being expressed primarily as iron sulfide. And then the development of that alteration facies is associated with low-grade nickel mineralization and some concentration of platinum group elements as well. And then this is adjacent to zone of strong magnetite alteration. So we can start to see emerging evidence that this style of hydrothermal nickel mineralization might be more widespread in these hydrothermal systems. Moving, as the system is evolving, now we're moving to a stage where we're adding potassium in conjunction with calcium and iron, and also in certain components where the association of potassium and iron will be expressed as a biotite-rich alteration facies. And this is typically associated with the concentration of cobalt to form metasomatic iron cobalt deposits. If we look at the mineralogy, typical minerals, we can still see amphiboles either as a residue or co-precipitating with biotite, component of iron oxides, magnetite, K-feldspar, or garnets are possible as well. And then one characteristic of cobalt-rich mineralization, very often it's going to be expressed as a concentration of sulfarsenides and arsenides instead of sulfides. Sulfides can be present too, but there can be a significant component of arsenides and sulfarsenide, exemplified here in the nickel deposits where cobalt mineralization is associated with the precipitation of cobalt in arsenopyrite, but also cobaltite and other sulfarsenides and arsenides. Other subsidiary minerals that are possible as well. Some uranium can become enriched at this stage, not always, but it could, and rare earths too can become enriched at this stage. If we look at the Nico deposit, so this is a Canadian example of metasomatic iron cobalt type of mineralization. If we look at the section along a drill core, what we can see is that the zone of gold, bismuth, and cobalt mineralization are associated with calcium, iron, and some potassium in the chemical signatures of these alteration facies, very typically associated with cobalt and then other element type of mineralization. And the expression of iron metasomatic activity for nickel varies from concentration of iron oxide, but there's also a component of iron silicate that can be associated with mineralization zones. The Blackbird deposit, the example from the Idaho Cobalt Belt, and here these examples are coming from the Merle deposit. And in the Merle deposit, one characteristic is that this iron rich metasomatic activity, instead of forming extensive iron oxide, it's going to preferentially form biotite in association with the deposition of the cobaltians of arsenites. These deposits are also complex because they've been remobilized and overprinted by many different stages of mineralization and alteration. And this has possibly resulted in a high grading of the deposit, benefiting actually mineralization. And this is illustrated by the very high grade cobalt that was present in the Blackbird deposit in association with copper and gold as well. But something that we can see is that iron in variable proportion is systematically associated with the formation of these zones of mineralization. Moving to the high temperature alteration facies and low temperature alteration facies, this is when we start to see copper coming in the mineralized system and start forming IUCG mineralization, but also other types of copper-rich mineralization like iron sulfide copper gold, for example. If we look at magnetite group, IUCG deposits, example from the Ernest Henry deposits, where we have this special association with magnetite, Cape feldspar, and the deposition of copper sulfides. And then this is evolving to a stage where carbonates are becoming quite important, transitioning to lower temperature alteration facies. And then carbonates with barite, magnetite, residues of Cape feldspar can also be associated with copper gold mineralization in the Ernest Henry deposit. But again, there's very strong association between iron-rich metasomatism and metal deposition. In Canada, we also have sensu stricto IUCG deposit. It's named the Soudayan deposit in Northwest Territories. Similar formation. So we have Cape feldspar alteration in the class, iron oxide forming the matrix. And in the Soudayan deposit, this iron oxide matrix will become variably mineralized by chalcopyrite to bornite, depending where we are in the system. Moving to hematite group IUCG deposits. Hematite group IUCG deposits, they're formed at lower temperature. One thing about lower temperature alteration facies, there's a very real explosion of complexity in the types of mineral assemblages that are possible at this lower temperature. And there's a wide diversity of expression of iron alteration and metasomatic activity at lower temperature. It's important to keep in mind, and it's also important to keep in mind which cation or which alkaline earth or is there carbonate or quartz that start forming, because this will have an impact on the type of metal that will be concentrated in conjunction with iron in these zones of low temperatures. And here, the minerals that are in red, listed in red, they're typical of hematite group IUCG mineralization that is characteristic of the Gawler Creton in Australia. So sensu stricto hematite group IUCG mineralization. But there's a wide suite of minerals that are possible as well at low temperature, associated with a wide diversity of potential metals that can be concentrated. If we look at sensu stricto hematite group IUCG mineralization, example from the Prominent Hill deposits, we have the resource number here for Prominent Hill. So extremely strong hematite alteration, and then different expression of copper mineralization can be chalcopyrite, but also chalcocite and bornite can become important copper sulfides. When they're mixed with hematite, they can be extremely difficult to visually see. So it's important if there is zones of strong hematite alteration to do analysis, because it can be hidden chalcocite in that, and this can result in extremely high grade copper mineralization. As the low temperature potassium iron alteration facies is evolving, it's transitioning from a hematite aluminosilicate to a quartz hematite type of assemblage. And generally what happened at this transition, the system switch from copper gold to gold-rich style of mineralization. And in the Prominent Hill deposit, this has led to the formation of a gold-rich zone that is kind of adjacent to the copper-rich zones that are currently forming the core of the resource of Prominent Hill. If we look at the counterpart of IUCG deposits, which are the iron sulfide copper gold deposits, in cases where iron-rich metasomatic activity, instead of being expressed as iron oxide, iron sulfide become the main expression of that iron-rich alteration. ISCG deposits, they can become significant exploration targets. In Australia, in the Cloncurry district, a good example of those is the Eloise deposits. This is the pre-mining resource, but the deposit keeps going, and that grew much bigger than what its pre-mining resource was. And really, the main difference with iron oxide copper gold is that instead of having iron oxide as hematite or magnetite, iron sulfide like pyrrhotite or pyrite becomes the main expression of that iron-rich alteration. What it also means is that geophysical methods like gravity and mag are not as suitable for exploring for this type of mineralization as electrical methods can be. There's also example of that type of mineralization in Canada, in the Romanech Horse at Delhi Pacific, where we have the formation of broad zone of copper mineralization in association with the deposition of iron sulfides accompanying the formation of the copper sulfide chalcopyrite and a little bit of bornite in association with the Delhi Pacific, showing overprinting an albitite. Uranium, in certain instances, instead of copper, will become the main metal concentrated at this alteration facies. A good example of that can be visualized in the Great Bear Magmatic Zone, where we have, in conjunction with the formation of magnetite veins, the deposition of uraninite. This is forming iron oxide uranium type showing. And this can be extremely subtle in certain instances, be more visually apparent than others, but it's important to break the rocks. This is the same rock broken. And what we can see is this network of magnetite vein in association with this uranium mineralization in the Great Bear Magmatic Zone, overprinting an albitite. So this rock is an overprinted albitite. If we look at larger expression of this albitite hosted type of uranium mineralization in the central mineral belt in Labrador, there are a good example of that. For example, the Michelin deposit, in which an albitite is variably overprinted by a little bit of magnetite, but really more hematite. And then this is associated with the formation of uranium mineralization in the Michelin deposits, and that's formed a quite significant resource as well, uranium resource in association with that uranium-rich mineralization. And then it overprints zone of strong sodic alteration. If we look at another deposits formed in the central mineral belt, we can really see the good special association. So initially this used to be a basalt. This basalt was extremely albitized, and then after its albitization was completed, it was overprinted by this iron carbonate, hematite, and uranium alteration that is associated with uranium mineralization. And interestingly as well, this provides a very good example of differential mobility of certain elements in the system. So for example, if we look at this zone of sodic alteration, we can see that zirconium is being enriched in comparison to what it was in the basalt, because it stayed behind and was relatively enriched. Whereas a metal like vanadium was kind of pushed out of the zone of sodic alteration, more on the shoulders as the rocks were becoming progressively albitized. Vanadium was less compatible and then was progressively pushed out of the zones. Another component of the low temperature facies are the metasomatic iron gold deposits. Scadding is a good example where we have an albitite progressively overprinted by iron metasomatic activity, and this led to the formation of our coeval formation of gold in association with the formation of iron-rich chlorite. And we can see the chemical signature of that rock here, in which iron is prevailing in the chemistry. And now what we can do is that we can have an association between certain types of metal enrichment and alteration facies that can help to guide us once we see alteration zones and mineralization zone in these hydrothermal system, where we can be in the system, and what type of mineral deposits or zone of mineralization can we expect depending on where we are, especially inside these large hydrothermal systems. The low iron component, molybdenum, the Merlin deposit is an example of that. It's a significant deposit. It's a very high-grade molybdenum deposit from in the Cloncurry district in Australia. No iron in association with molybdenite mineralization. Copper and gold. Mondor with very little iron, but a filling of carbonate and some tourmaline in association with chalcopyrite mineralization. Some other example from Australia with carbonates and the deposition of copper, but also potentially of cobalt. And then in the Romanech horst as well with dolomite or carbonates associated with the formation of chalcopyrite mineralization. Gold at the Tickhill deposit. Tickhill in itself, it's still a significant deposit, very high-grade gold deposits, about 500,000 ounces at very high grade, with low iron type of alteration facies associated with that mineralization. If we have hybrid deposits, generally it's because there's different alteration facies that are formed and are overprinting each other. The Nico deposit is a good example of that in Northwest Territories. When we look at Nico, we have an initial skarn stage associated with tungsten and high temperature calcic potassium iron and biotite rich high temperature potassium iron associated with arsenic, gold, bismuth, cobalt, minor copper, and then an overprint by sensu stricto IUCG mineralization associated with the copper, gold, and silver component. So Nico is really a good example of how the temporal development of these different alteration facies and overprinting relationship can concentrate in the same deposit, different metals. But then how to classify that, it's really what is a primary metal in the zones of mineralization on an economic perspective to define what type of deposit we have. I think that will be it. So thank you very much.
Thank you, JF. That was a great talk. Does anyone have any questions? You are welcome to unmute yourself to ask JF, or you can send it in the chat.
Hi, I have a quick question. JF has told us basically how chemistry and temperature affect the different type of mineralization and brought in the importance of structure in some of his examples as well. I just wonder about the influence of host rock, because for example, being in Sudbury here and knowing a little bit about scadding and Fostung, they're both in very similar stratigraphy within the Huronian supergroup. So I wonder if there's relations like that elsewhere in the world.
Yes, I think the host rocks are going to imprint part of the signatures of the mineralization zones that can be formed in these hydrothermal systems. They tend to remobilize the crust in which they are formed. And then if there are certain assemblages of metals that are pre-concentrated in the geological environment, there's a likelihood that these metals can be concentrated in the mineralization zones that are formed amongst these systems. For example, cobalt-2 seems to be more preferentially concentrated in sedimentary units than in intrusive system or in intrusions. In Brazil, where jaguar and jatoba are formed, there's a lot of mafic, ultramafic rocks in the geological environment. So this may have contributed to the nickel endowment of this part of the mineral system. Near Sudbury as well, what is interesting at scattering, for instance, and a lot of showings that we can see, there is a very ubiquitous nickel enrichment in many zones of mineralization. It's not high, but it's systematically present, probably related to the Sudbury igneous complex that it's in close proximity, but also the knowledge that some of the nipissings are mineralized with nickel. So it's not something surprising to see that. So yes, the geological environment can have an imprint and an influence on the type of mineralization that can be formed at the end.
And that's true that at Scadding, you can see the albitization affecting some of the Sudbury breccia that cross-cuts the stratigraphy there.
Yeah, it really becomes the Sudbury breccias. They're becoming zone of rheological weakness. So when scadding is formed during a strong deformation event, that postdates the formation of the Sudbury igneous complex. And what we can see is that the Sudbury breccia can become preferential corridors of deformation, but also of mineralization. So they can be important in that respect to focus fluid flow and enhance the concentration of metals.
Any other questions? Okay, well, if there's no more questions, I wanted to thank JF again for taking the time to give us this presentation, as well as everyone else for joining. I'd like to give a quick little update. Next month is going to be our first in-person meeting. We'll do a combination of in-person and through Teams. So those of you that cannot make it in person are still welcome to join in from home, and Ed will send more details following that. It'll be Magna Mining presenting some of their new exploration that they've been doing.